Today we'll continue with the same topic, which is the robotic arm link velocities, and we will consider an example. This is a summary of the formulas that we derived in the previous lecture. We considered two cases, one in which the joint between link I and link I plus 1 is a revolute joint, and in that case this is the formula for the linear velocity of the origin of the frame of link I plus 1, and this is the formula for the angular velocity of link I plus 1. For the other case in which we have a prismatic joint, meaning that link I plus 1, or this part of link I plus 1, will move and translate along this axis. In that case, the linear velocity of the origin of the frame attached to the link would be expressed using this formula, whereas the angular velocity of the link would be given using this formula. We will consider a very simple example here. We have a planar, 2 degrees of freedom, RR robotic arm, and by planar I mean that all parts of the robotic arm will remain in the same plane during motion. And 2 degrees of freedom, these are corresponding to the two joints, joint 1 and joint 2. And it's an RR, meaning that both joints are revolute joints. So we have theta 1 and we have theta 2. Both of them are rotations about the out of the plane axis, which is in this case going to be the Z axis. So, and we are required to calculate the velocity of each link. We have link 1, this is link 1, and we have link 2. And also we are required to compute the velocity of the end effector. This is the end effector here. And by compute, I mean to express the velocities in terms of the joint rates, which are theta 1 dot and theta 2 dot. From forward kinematics, we could easily obtain the homogeneous transform matrices. This is the homogeneous transformation matrix for frame, describing frame 1 with respect to frame 0. As you can see on the robotic arm, we have frames attached to it. We have frame 0. You can see x0 and y0. This is attached to the base. It's stationary. It doesn't rotate or move. We have frame 1, consists of, here we can see x1 and y1. Of course, z1, according to the right-hand rule, will be pointing out with the page. It is this frame 1, is attached to link 1 and rotates with it. We have frame 2. We have the x-axis of frame 2, x2, is pointing along link 2 and it rotates with it. And finally, we have frame 3, which is attached to the end effector. We have no joint here, so we have intentionally have assigned frame 3 to be parallel to frame 2. In that case, the transformation matrix would look simpler. So, if you look at the transformation matrix T1 to 0, this matrix describes the orientation and the position of frame 1 with respect to frame 0. So this part of the transformation matrix here includes the rotation matrix of frame 1 with respect to frame 0. And what we can see is that this is the basic rotation matrix for rotation about the z-axis and by an angle of theta 1. And this makes sense because you can see frame 1 is rotated from the orientation of frame 0 by an angle of theta 1 by counterclockwise about the z-axis. For the transformation matrix of frame 2 with respect to frame 1, the corresponding rotation matrix also includes the basic rotation about the z-axis, but now with an angle of theta 2. So the notation we have here is C1 is in reality the cosine of theta 1. C2 is the cosine of theta 2. However, we wrote it in this way to make it simpler and reduce the space because we are limited with the space, either if it was in the slides or in the notes. So again, you can see for frame 2, it is rotated with respect to frame 1 by an angle of theta 2 about the z-axis. Finally, for frame 3, since it's parallel to frame 2, you would expect to find the identity matrix here. And if you look at the last column of each of these matrices, this one, for example, the 3 entries here correspond to the x, y, and z of the origin of frame 1 with respect to frame 0. So you can see that since both of them are at the same point, so this is going to be 0, 0, and 0. So here, the origin of frame 2 with respect to frame 1, we can see that this origin is translated with respect to the origin of frame 1 by the length of link 1, and we call it L1, and it's along the x1 axis. So it's here L1 and then 0, 0. 0 in the y direction and 0 in the z direction. And finally, for the last frame, frame 3, again, in the same way, it is translated along the x2 axis by an amount which is equal to the length of this link, which is L2. One thing that we will do here is to extract the information, as we did before, for the rotation matrix from the transformation matrix. So this is for T10, we can get R10. From T21, we can get this rotation matrix, and from T32, we can get this rotation matrix. At the same time, we also can extract the positions. So this is again the position of the origin of frame 1 with respect to frame 0. This is the position of frame 2 with respect to frame 1, and this is the position of frame 3 with respect to frame 2. Furthermore, we need to identify that since all of the joints here are revolute joints, there is no need to consider the formulas for the prismatic joint condition, and thus we only need to consider these two formulas in this example. So I'm trying to put all of the required information in one slide. So here we have the formulas that we need to apply. We have the rotation matrices, the ones that we extracted from the transformation matrices, and we have also the position vectors for all of the three frames. In this slide and in the following ones, I have divided the slide into two sections. The section in the right would contain the same information for all of the slides. It would contain the formulas, in this case for the revolute joint. This is the formula for the angular velocity. This is the formula for the linear velocity. I also included the skew symmetric matrix, the definition of the skew symmetric matrix, and we also have the rotation matrices for the case considered in this example and the position vectors. So we want to have this handy for the rest of the slides. Now we start with applying the formulas by substituting values for I from 0 up to 2. So if we substitute for I with 0 here, this becomes the angular velocity of link 1, and here we'll have R of 0 with respect to 1, and this is going to be the angular velocity of 0 or the base, and here we will have theta 1 dot, which is shown here. Now we start substituting. So for R01, this is in fact the transpose of this rotation matrix, R10. This is why we have the transpose simple here. And we have the omega 0, which is the angular velocity vector for the base. And the base, since the base is stationary, we are assuming for this example that the robotic arm is fixed on a table. So it's not attached to a rover or a drone. It's simply fixed to a stationary table in the workshop or in the lab. So omega in the x and the y and the z for the base is going to be 0. Then I have the this part, which comes again from the formula itself. So it comes here. So what do I need to do? I need to do to compute the product of these two matrices, since this is a 0 column matrix. So the whole term here is going to be equal to 0, and then omega 1, which is the angular velocity of link 1, is simply going to be equal to this vector, which represents a rotation about the z-axis by an angular velocity of theta 1 dot, which makes sense. So link 1 will be only affected by the joint rate of joint 1. Now we're going to look at the second formula, the one for the linear velocity here. So you can see that if we substitute for I with 0, this becomes V1, and this becomes R of 0 with respect to 1, and this is V0, and this is the skew symmetric matrix for the 0 omegas, and this is the position of 1 with respect to 0, which is what we can see here. So then again, as before, R01 is the transpose of this matrix, and the V0 here is simply the linear velocity of the origin of the frame 1, frame 0, which is the base frame. Again, this is not moving, so it's going to have a value of 0 here. And then the skew symmetric matrix of the angular velocities of the base, again, because 0 represents the base, and since the base is not rotating, so if we can substitute for omega x, omega y, omega z in this matrix with zeros, and thus the whole thing is going to be zeros. Then the position of the origin of frame 1 with respect to frame 0, you can see that we can have it here, and we already see that frame 1 has the same origin as frame 0. So this whole part here is going to be 0 multiplied with this will give us a 0, which makes sense again. So this simply means that V1 is not moving. So now I added one more section to this slide. In this section, the one here in orange, I can see the results from the previous iteration. So this is from the case where I was equal to 0, where we were able to obtain the angular velocity of link 1 and the linear velocity again of the same link. And here we have the computations done by proceeding to the next value of I, So now I is equal to 1. We substitute into this formula for the angular velocity as we did before. So we will have the angular velocity of link 2. We will have R1 with respect to 2, the angular velocity of link 1, and from the formula itself we have the vector which depends on the joint rate of joint number 2. So R1 with respect to 2 again can be found here, is going to be the transpose of this matrix. So I take this one here, but I have a superscript of T representing the transpose. Omega 1, where do I find this? I can find it here from the previous slide. I already found that omega 1 is going to be 0, 0, theta 1 dot plus the term from the formula itself. So we just bring it here. So now I need to find the transpose of this matrix. This row becomes a column. So cosine 2 becomes here, minus sine 2 here, and 0 comes here. For the second row, I have sine 2, cosine 2 comes here, and then 0, and finally 0, 0, 1. I have to multiply this by the vector and then add it to this vector. Now the multiplication here is done straightforward. You take it row by column. So you have cosine 2 by 0 plus sine 2 by 0 plus 0 by theta 1 dot, which gives me 0 here. The second row in the same way will get another 0, and the last row by this column will give me theta 1 dot. So I have two vectors now, or two column matrices I can add together to get the omega 2, which is the angular velocity of link 2. One thing to notice that I had a superscript of 1 here, meaning that theta 1 dot was about the z1 axis. However, after multiplying it by this matrix, it became now the superscript became 2. Why is that? It's simply because this matrix is the rotation matrix from frame that describes frame 1 with respect to frame 2. And when I pre-multiply it by another matrix, so it's another vector in this case, this is exactly the definition of mapping. So here what we are doing is mapping from frame 1 to frame 2, as if the 1 is cancelling out with 1, and then it becomes with respect to frame 2. So both of them now are in the same expressed in the same frame, and thus the angular velocity of link 2 is going to be given by this vector. So link 2 now has an angular velocity which really depends on theta 1 dot and theta 2 dot, and both of them are about the z-axis. So you can see that the results make sense, and in fact you could reach the same results by inspection without really going through the whole procedure. However, this would only apply for a simple case as in this example, but for a much more complicated case where you have let's say more degrees of freedom, for example you could have a 6 degrees of freedom robotic arm, it will be difficult to figure out the velocities just by inspection. This is why it's important to understand and follow the procedure as we are doing in this example. So now the result that we got here, we are going to take it and add it to the blue section of the slide, or in the blue box of the second slide. So you can see now in the orange box here, we have omega 1, v1, and omega 2. So here is in the orange section we have the results obtained so far for link 1 and the angular velocity for link 2. Now we'll continue with I equals 1, but now for the linear velocity. And the linear velocity is obtained again by substituting the value of I, which is 1, now in this formula. So this becomes v2, and this becomes R1 with respect to 2, and this is V1. And this is the skew symmetric matrix of the omega 1. And this is P2 with respect to 1, as shown here. Now we substitute for the values R1 to 2 again, as in the previous slide. This is simply the transpose of the rotation matrix we have here. So we have the superscript T. V1 is the linear velocity of link 1, and we already obtained this from the previous iteration when I was equal to 0. So we have it here. So we substitute, so it's all zeros. All of the values are zeros here. So this is V1. And what about the skew symmetric matrix? Skew symmetric matrix of link 1 can be computed by substituting in the general formula of the skew symmetric matrix, where omega x, omega y, omega z can be obtained from the angular velocity vector that we obtained before. So instead of omega x here, this is going to be 0, this is going to be 0. For omega y, we also have 0. We substitute 0 here, 0 here. And for omega z, is going to be theta 1 dot. So we have theta 1 dot and theta 1 dot. And so this is the skew symmetric matrix for link 1. This is multiplied by P in the position of frame 2 with respect to frame 1, which we extracted before. So we have it here. So we start by first of all finding the transpose, and this is straightforward. And then we need to multiply these two matrices. You can directly see that we'll have a 0 here, second row. By this one, we're gonna have a theta 1 dot L1 in the second row, and the last entry is gonna be 0. All of this, when added to the 0 vector here, then all of this should be pre-multiplied by this matrix. Again, because it's a rotation matrix, we have mapping, and we'll be mapping the results from frame 1 to frame 2 as represented by the superscript. So we just do the multiplication, and so you can see cosine 2 by 0 plus sine 2 by theta 1 dot L1 plus 0, and this is the first row here. For the second row, we'll have cosine 2 theta 1 dot L1. The last row will have a 0. So basically, this is the velocity of the origin of frame 2, which is attached to link 1. This is so it's basically the linear velocity of this point here, the one I'm pointing at, which is the origin of frame 2. Now this result, we will take it and add it to the results section in the next. Now you can see we have the angular velocity of link 1, the linear velocity of link 1, the angular velocity of link 2, and the linear velocity of link 2 as obtained in the previous slides. Now we move to the next value of I. I is equal to 2. As before, we need to substitute in the angular velocity formula. We have omega 3 and R3 with 2 with respect to, it should be R2 with respect to 3, that's correct. And we have omega 2, and here we have 0, 0, theta 3. Now, there's a tricky part here, just I want you to pay attention to this. So if we substitute I2 here, so it becomes theta dot 3. But if you look at the example, we don't have a theta 3. The last frame is attached directly to the end effector. So it's always going to be 0. So this, I have it highlighted in red. So this is 0 here. Now we substitute in the values R2 to 3, which is the transpose of this matrix. and the omega 2 is the angular velocity vector as obtained in the previous iteration. So 0, 0, theta 1 dot, theta 2 dot. Now we just need to, the transpose of the identity is again the identity, and anything multiplied by the identity is going to stay the same thing. So this is omega 3, which is the angular velocity of link 3, which is the same, which has the same value as the angular velocity of link 2. Now we're going to look at the linear velocity. So we're continuing with the value of I equal to 2. We're looking at the linear velocity now. You can see that V3 is going to be equal to R2 with respect to 3 as before, V2 and the skew symmetric matrix of the angular velocity of link 2 multiplied by the position of frame 3 with respect to frame 2. And we substitute in the values. R23, we already saw that it is the identity matrix, and it's the transpose of this, which is still going to be the identity matrix. V2, which is the linear velocity that was computed before. So we just bring it down here. And skew symmetric matrix is by taking the values from the angular velocity of link 2 here and substituting them into the general form of the skew symmetric matrix. Again, omega x, omega y, both are going to be equal to 0, and omega z here going to be equal to theta 1 dot and theta 2 dot. So this is the skew symmetric matrix for link 2. And finally, this is the position of frame 3 with respect to frame 2. We have it here, and you can see we need to do the multiplication of these two matrices. The first row by the first column is going to be 0. The second row by this column is going to be theta 1 dot plus theta 2 dot multiply L2 as we find here. And the last one is going to give me a 0. Then I just add up both of these two vectors, which is this one and the product of these two, to get the result here for the linear velocity of the origin of link 3, or in this case of the end effector, because the link 3 is the end effector in this case. So here we have a summary of the results that we obtained so far. This is the angular velocity of link 1, the linear velocity of its origin, angular velocity of link 2, and so on. And by this we end the example, and we'll see you hopefully next lecture when we cover a new topic. This is another example where we have a 2-degree of freedom robotic arm. This is a PR robotic arm where we have one revolute and one prismatic joints, and we need to find the velocity of each link and also that of the end effector as a function of the joint rates, being theta 1 dot and d2 dot. Here we have the transformation matrices representing the orientation and position of each frame with respect to the one before it. And here we extract the rotation matrix for each one of them, this being our frame 1 rotation matrix of frame 1 with respect to the base frame. This is for 2 to 1, and this is for frame 3 with respect to frame 2. Here we extract the positions. This is the position of the origin of frame 1 with respect to frame 0, and so on. These are the formulas. These two equations, again, these are for where we have a revolute joint. In case if we where we have a prismatic joint, we need to use these two equations. So we'll proceed with the solution in a similar fashion as we did before. We're going to divide the slide into a number of boxes. In the black box here we have the formulas, and we have this is the formula, two equations for revolute joint, two equations for a prismatic joint, the skew symmetric matrix, the rotation matrices, and the positions. And we'll have this in the coming all of the coming slides. And here in the green box we will have the calculations as we proceed from I equal to 0. So I'm not going to go in details as we did before. I just need to substitute I into the formula. Now for the first joint, so where I is 0, so we'll have joint 1, and we already know that joint 1 is a revolute joint, so we need to use these two equations. When we substitute I equals 0, we'll be able to compute omega 1 and V1. And it makes sense that V1 is going to be equal to 0, as frame 1 has its origin attached to the origin of frame 0, and this will not change, so it will gonna have a linear velocity of 0, and the angular velocity is going to be 0, 0, theta 1 dot. Now, so in the orange box here, we will have the result from the previous slide. So up to now we have the angular velocity of link 1, and we know the linear velocity of the origin of frame 1. Now we proceed with I equal to 1. I equal to 1, this corresponds now to joint 2, and joint 2 is a prismatic joint, so we need to use these two equations now. So starting with the angular velocity, so this is the simple relationship that will give me the angular velocity for link 2. We just substitute as before for the rotation matrix. For the value of the angular velocity as we obtained before, we just bring it down here. We do the calculation and it turns out to be 0, theta 1 dot, and 0. So omega x, omega y, and omega z. Now we substitute into the second equation, for which we're going to find the linear velocity of frame 2. And in a similar fashion to what we did before, it turns out to be theta 1 dot, d2 0, d2 dot. So now, up to this point, we were able to find the angular velocity and the linear velocity for both link 1 and link 2. Now, if we proceed and substitute for I equal to, you will find out that we're talking about joint 3, but we don't have a joint 3. In fact, we have the end effector now, and the end effector is neither revolute nor prismatic. In that case, so we have the option either to use these two equations or these two equations, but it's very important to make sure to delete the joint rate. So if we are going to use the equations for a revolute joint, for our case, which is the end effector, we can use these two equations. However, taking into account that this should be removed, theta dot, there is no theta dot. And if we are going to use the prismatic joint equations, we can do that as long as we also neglect this part, d dot. So in both cases, we'll get the same two equations. So for the omega 3, we're just going to get r, in this case, r times omega. And you will see that the angular velocity of link 3 turns out to be the same as the angular velocity of link 2, and this makes sense as frame 3 will always be parallel to frame 2. So they must have the same value for the angular velocity. And here, when it comes to the linear velocity, we'll do the same thing. Either we take this equation without this term, or we take this equation, which is the same. And we substitute in the values from the previous box here, and we can find the value for V3, the linear velocity of the origin of frame 3. And you can see the how it relates to the angular velocity of frame 2. Very similar to it, we just added one term due to L2. So as a result, for this example, following the procedure propagating for the velocity from I0 to I2, we were able to find the angular velocity and the linear velocity for each of link 1, link 2, as well as for the end effector. That's it for today. Thank you.